I'm laughing at her. I
There's
think.
like a curtain between you.
What is somebody doing?
I don't even know.
Why are you doing that?
I'm trying to keep them from seeing each other. Just
Oh. I'm good. I'm good.
They're
I'm
disturbing
focused. Do sequences have to go to infinity?
You can have finite sequences, but then you don't get the same theorems applying, like the one you do with the grains of sand.
Right.
You got a series there, it's a sequence of numbers you added up. But since it doesn't go to infinity, you never have to worry about some of these nuances I was talking about, like if you interchange the order and
Right.
a different sum. So yeah, there are such things as finite series, but they're not as useful as the infinite series, and you guys will see why. We'll do all kinds of applications with this. Luciana, before you leave Stetson, I want you to take a class with Dr. Will Miles.
Dr. what?
Will Miles,
Calc 3 in the fall.
M-I-L-E-S.
And what?
Miles. Take his class. Take Calc 3?
Probably.
You taking that class?
Do they have it in the summer?
No, in the fall.
I don't think I could fit
No.
it.
I want you to take him as a teacher though.
Doesn't he teach something else like theoretical?
Because he is a teacher who cannot stay on task for the life of him, and I think it would be amusing to have you in his class.
You really can't.
Awesome.
I
You
would
can't-
want
I
to
know-
be in there.
He can't stand what?
He can't stay on task. Every 5 minutes he's talking about college basketball or how
Clemson.
Math is awesome or Clemson or something.
Clemson is awesome.
No, not really.
He's an amazing
He's a
teacher.
great teacher.
We all got
Talking
A's.
about his life or whatever.
Yeah, and I just think it'd be amusing to see how you interact with that. That'd be awesome, actually. I'd pay to sit.
I came into
I
class.
would pay to sit in that class.
Does anybody else teach the Calc 3 class?
Yeah, I do.
Oh, okay.
Yeah, but that wouldn't be as fun, you know what I mean?
Yeah, but you would have to wait till like
I
your
might-
senior
Yeah,
year
I know.
spring.
Then I might as well just teach myself from the textbook and not go to class. If he's just going to be talking about.
Yeah, well, there's something to say for the amusement that's provided.
I don't think Luciano comes to this class for the amusement.
No, I think you're right.
I went into class, or I had him for Calc 1 over the summer. I kid you not, I went into class 40 minutes late and they hadn't started yet.
Yes, that's what I'm talking about. That's exactly what I'm talking about. Yes.
But he still managed to teach us everything.
Yeah, oh sure, sure. That's why he's good at it.
I learned all about Clemson.
I think if you were on, like, didn't joke around at all, Dr. Noble, I would probably fail this class.
Yeah, I don't think I could do this job if I took it that seriously. I don't know how some instructors do, but.
Because they're psychos,
Could name a few.
for sure.
Alright guys, first big theorem in series, right here. Now this only works on a very limited class of series. And you'll see, to Christian's point about You know, when I put that sequence generator up there, he said, you know, if you just give me the elements of the sequence, it'd be really tough to identify that. And that's kind of the situation you get involved with here, because you have to be able to reconstruct the sequence generator in order to do it. So there's only so many examples we can actually work through this with. But the ones where it works, it actually really works well. Let me give you an example of this. Now, to begin with, can anybody tell me why I started from 2 and not 1?
If you start at 1, it's 0.
Yeah, if you start with the 1. So you'll still see the index on the sums parity that of the sequences, with them being natural numbers. But there are times, based on the structure of the series itself, where you can't start from 1. Maybe you can't even start from 2, right? So there's kind of a natural domain associated with this. Well, what I'm saying over here with the sequence of partial sums is if we turn this series into a sequence by looking at all of the various terms of these partial sums, if we can find a limit to that sequence, then the limit to that sequence is going to be the same as the limit of these partial sums. In fact, you know what? I know you're writing, and I apologize, but let me try an easier one. Well, I'll do that one next, but let me try an even easier one. One that we've already seen play out. You guys remember the answer to this? This is equal to
1.
1. This is the one, yeah, this is the box that I did. Half the box, and then half of that, and then half that. So let me actually evaluate it using this theorem now. So when you look at the various terms, the A1 is just going to be a half. That is the first term. So S1, S1 is what it's saying. Right. The S2 is going to be a half plus a fourth. In other words, the sum of the first 2 terms, right? So we go ahead and add those together, and you get 3/4. Continue this process, at least for a couple more. Right, so it's an eighth plus a fourth, so it's 7 eighths.
And after you've done 3 to 4 of these.
Yeah, I did. Second question?
So you're saying after we've done 3 to 4 of these, chances are pretty good that we'll be able to see.
Then you got to figure out a formula for those elements of the sequence. That's exactly right. So this is going to be 15.
So we're trying to find a formula for the
For the sequence itself, the sequence of partial sums.
Ah, okay.
Right. So if you look at the result we're getting here, you can start to form the sequence. Right. This is a half, 3/4, 7 eighths, 15/16, and it continues out. Right. What we need to do is construct a representation for the S of n. That is the nth term of the sequence. Because you see, that's how the theorem works. Once you find that S sub n and you take the limit, whatever limit comes out of that is what the series adds to.
So is that the last term?
No, there is no last term. It's the nth term.
So what is the nth term?
Well, you tell me that. Look over here. This is the pattern recognition I was talking about. And this is one of the reasons it becomes relevant. See, what I have is a sequence made up of terms that are partial sums of the series itself. So what we need to know is, what does the nth term look like?
What do you mean by the nth term?
Well, if I were to say, what is the 97th term in the sequence, I want you to give me an answer.
The seventh term?
97.
Oh, no. Well, I don't want to do the work right now.
Well, that's what I'm asking. But that's what, so to find the nth term means you can plug an n in and actually
Oh, so
get
it's
what the
the
number
term.
is. It's a function of that, right? That's why I define a sequence as a function whose domain is the natural numbers, because then it makes more sense. But if you look at these denominators, 2, 4, 8, 16 for 1, 2, 3, 4, how does that work?
They're all 2 to the n.
They're all 2 to the n.
So,
The top works except for, like, can't figure out how to do the first one. So you could do n minus or do n